Everyone should have the handout Exploration 1-3A, Introduction to Definite Integrals. So we're working on finding out what a definite integral is. We're starting with a situation where we have a car driving on the highway and we are at 100 feet per second because we're passing a truck, and after you pass you slow down to a more moderate 60 feet per second. The diagram shows the graph of your velocity v of t as a function of the number of seconds since you started slowing down. So our v of t is on the y-axis, and I'm going to go ahead and put my units here just so I know what this is. The units for my velocity are feet per second, and on the x-axis I have that labeled as t, which is time, and in this situation we have that in seconds. So I've got my graph labeled a little bit better than I started, and we need to go ahead and start with question 1. What does your velocity seem to be between t equals 30 and t equals 50 seconds, and how far do you travel in that time interval? So when I look between 30 and 50, let's see, here's 30. Don't ask me. Here's 30, and it looks like my velocity is 60, and here's 50, and it looks like my velocity is 60. Okay, so I can actually treat this not like a calculus problem. Let's treat it first like a problem we would have done a long time ago, probably in middle school. And we know that distance is equal to rate times time. So we can go ahead and use that here. We have a rate. It seems that the rate during this entire time interval is 60 feet per second, and we know that the time between 30 and 50 is 20 seconds, and that comes out to be 1,200 feet. So my velocity, sorry I didn't actually write that all down, my velocity is approximately 60 feet per second. And then how far we traveled in that time interval is 1,200 feet. So number 2, explain why the answer to problem 1 can be represented as the area of a rectangular region of the graph. So when I was drawing on the graph, I basically did make a rectangle. And go ahead and draw in my base. So I do have a rectangle, and that rectangle, when I shade it in, is right here. There's my shaded rectangle. And I need to explain why the answer to problem 1 could be represented as that area. So basically what I did is I took the height, and the height of this rectangle is my y value, which is 60, and I multiplied it by my width, which we had already calculated that was my 20. And when I take 60 times 20, it gives me 1,200. So I need to write that down, and I need to explain that somehow. So what I'd like you to do right now is I'd like you to pause the video, write down your explanation, and after you have your explanation, play the video again to see what I have written down. Go ahead and pause right now. So my explanation talks about the change in time is 20 seconds, and that's on the x-axis. And the change in velocity is, well, the velocity doesn't change, it's constant at 60 feet per second. So I'm just taking the height times the width, which is 60 times 20, which gives me my 1,200. Number 3, we're now looking at the distance that we travel between t equals 0 and t equals 20. And again, that's represented as the area of a region bounded by the curved graph. So what we're going to do is we're going to estimate this by counting the squares in this region. So I'm actually going to start at the last question, which is, for instance, how would you count this partial square? So in looking at this shaded square, it looks like it's close to half, but I think it's a little bit bigger than half. So I would estimate that at probably 0.6. It's not one full square, it's a little bigger than half. So I would say that's a good estimate. Now again, these are all going to be estimates right now in number 3. We may get different values, and that's okay, as long as we're within the realm. We don't want to be too far off. So I'm going to go back up to my graph now. And I'm not worried about what I previously did. I need to be looking at between 0 and 20. So the easy part is let's go ahead and figure out, we've got some squares here. And right here, we have one big rectangle, and the number of squares is 24. So we've got 24 squares right here. Then we've got to count up the rest. The one right above the 60, excuse me, this is going to be my 25th square. And again, we're estimating. So I think that these two squares that I've put dots in, they seem to be missing about the same amount. I think they're a little bit larger than 0.9, but they're not quite 1. So I'm going to go ahead and call one of them 0.9. I'm going to call one of them 1 just to balance it out. Then we need to kind of estimate the remaining squares. When I look at this one right here, this is the one that we were estimating in problem 3, and we estimated that to be 0.6. So I'm going to call that 0.6. I'm going to call that little tip right above it, I'm going to call that one a 0.1. And this other tip down here, I'm going to call that one a 0.1 as well. And then what we have is these two little things. And I'm going to estimate that we have this as about 0.4. Because I don't think that's half. I think it's a little bit less than half. And then this little bit right here, this little triangular region, I'm going to say that's about 0.3, 0.2. And now I need to add that all up. So grab your calculator, add up everything that we have, and let's see if we get the same number of squares. When I added that up, I got the total number of squares to be approximately 28.4. So I'm going to write that down for number 3. And I have approximately 28.4 squares. And again, we should be within the realm. We know it can't be 30. I think 27 would be too low. So somewhere between those two numbers would be good. Question 4. How many feet does each small square on the graph represent? Okay, so we've got a square on the graph. Let's look at the x or the t value. When I look at one little square on the graph, I need to figure out how far across is that. And all the up to 10 goes here, which means this little squiggle has to be 5. So I've got a 5 on the x-axis, and let's look at the y-axis. And again, I just want one right here, but I know all the way up to here is 60. And I've got 1, 2, 3, 4, 5, 6 of those, which means each one must be 10. So I've got 10 right here, which means if I want to know the area of a single square, that area is going to be 50. So how many feet does each small square on the graph represent? Okay, so it really means 50 feet. So then it's asking how far did you go in the time from 0 to 20. So I've already counted the squares and I got 28.4, and now I know that each square is actually 50 feet. So I'm going to multiply those together. So I take 50 and I multiply by 28.4 and I get 1420 feet. Again, that's an approximation. It is an estimate. Number 5. For problems 3 and 4, they involve finding the product of an x value times a y value. And such a product is called a definite integral of y with respect to x. So based on our units that we have for time and velocity, we need to explain why the definite integral with a v of t with respect to t has feet for its unit. So you go ahead right now and explain that in words, and then so hit pause, and when you are finished, check and see what I have. So with y being the velocity, which is in feet per second, and x being the time, which is in seconds, when I multiply the y value times the x value, I take feet over seconds times seconds, which when I multiply that out would give me feet seconds all over seconds. And of course my seconds reduce out, they make a 1, leaving me with just feet. Now number 6, we now have a cross-sectional area of a football. And we're trying to estimate the definite integral of y with respect to x. So what I want you to do right now is go ahead and you count up your squares, figure out how many squares you have in total, and pause the video. And when you unpause it, it will have the number of squares on it. So pause it right now to count. I estimated there were approximately 45 squares. The parts in the middle that were full squares are fairly easy to count, but let me go through how I counted the remaining squares. When I looked at the pieces right here, they looked to be like that could have made one square. So I'm going to count that as one square. And I'm going to do the same thing because it's symmetrical. I'm doing the same thing on the other side. From there, I'm going to do exactly what I was doing. I'm going to match up pieces that I think look like if they went together would make ones. Or you can do it exactly like we did before, which was we're just saying these are pieces up to point 0.1. I called this one square, which means I did the same on the other side. I counted the ones above this one square. I thought that these approximately here and here together would make one square. I went ahead and decided that I thought that the small piece at the bottom would match up nicely with this little smidge of a piece right here. It makes that a 1. Same thing on the other side. So this little smidge of a piece and this, I decided that was approximately a 1. And then I thought up here we had an additional 1 together. Find a good color. So I thought these two on the right and on the left, I thought together made a single 1. And when you add that up, you should get 45. Now each square, the area of each square on the whole grid would be going on the x-axis is a 1, but going on the y-axis, I believe, is going up by 5s. So the area of one square ends up being 5. Now, what I have discounted here is I did not discuss units, and I did not simply because I know it's in question 7. Normally, I wouldn't ask you a separate question about the units. It would be expected that you would put the units in to the original question. So number 7 is saying, what are the units for the definite integral in problem 6? So the units for this one are going to be the y-axis units times the x-axis units. So let's go back to the original question. So the units for y are in inches squared. So we're going to have inches squared, and we're going to multiply those by the x units, which I circled over top of, and the x units are in inches as well. So we have our y units in inches squared, and our x's are in inches, which means when I calculate the definite integral, the units for that are going to be inches cubed. What therefore do you suppose the definite integral represents? Well, with my units being inches cubed, I'm confident that the definite integral represents volume. So in number 8, I would like you to write, you can just put a bullet down. What did you learn as a result of doing this exploration? And we are finished with this video lesson.